So solving linear systems. Before we jump into solving linear systems, let's take a second and let's just think what it means to solve anything, right? Like just take this blue equation right here. Simple equation, it's a linear equation in one variable. It's only got one type of variable. What's the solution? What's the solution? Yeah, right? Yeah, good. So, I mean, we would just add 1 to the other side and divide by 2, right, to isolate the x. And we would get x equals 4. Why is that the solution? What's it do that makes it the solution? How do we know it's the solution? Okay, good. When you plug it in for x, it makes it true. Exactly. So this is the value of x that satisfies the equation. In other words, it makes it true, right? Well, what if we had something, let's take the red equation. Now, the red equation has 2 variables, right? So the red equation, a solution of the red equation is going to involve values of x and y. So what if I pick, now this is going to be maybe kind of different a little bit. If I pick a value, like let's just say I pick x equals 3. What value of y would have to go with that in order to satisfy that red equation? What would it be? Not -6. How could we find out? Well, if I plug an x value of 3 in there, I'm going to get 2 times 3 minus 3y equals 12. Well, that's just 6, right? That's just 6. So if I were to subtract that 6 to the other side, I get negative 3y equals 6. So what would y equal? -2. Okay. So there's one value.
All freshmen, it is now time to go to your bus evacuation. Teachers, please take them out. Thank you.
Forgot we had that today. I hate this day. So the ordered pair 3, -2 is a solution of the red equation because it satisfies the equation, right? But there could be others. Like what if I pick x equals -3? Well, what happens then? If x is -3, I get 2 times -3 is -6 minus 3y equals 12. Now to solve for y, what would I have to do? Isolate the y. Good. So I'd add this 6 to this side and get -3y equals 18. So what would y equal this time? -6. Okay, how many? So there's another solution, another ordered pair that acts as a solution of the red equation. How many ordered pairs could I come up with? An infinite number, right? There's an infinite number of ordered pairs that would satisfy this red equation. Let's look at, like, what if I wanted to represent all those ordered pairs graphically? What would that look like? What would that look like? Okay, well, there is the red equation. If I graph that, it's a line. Where do you think the values, or the ordered pairs 3, -2, where do you think that's going to end up? Yeah, it's just on the line, isn't it? And if I graph with that the ordered pair -3, -6, that's just another point that's on the line, right? So that line is really just a collection of an infinite number of ordered pairs, right? And we've talked about this a little bit, right? It's an infinite number of ordered pairs that string together all those points to create a line, right? Okay, the same thing would be true for, look at the green equation here, y equals -x plus 1. Okay, if I turn off the red line and I turn on the green line, again, that green line is just a collection of an infinite number of ordered pairs. It has infinite solutions, right? Okay, but what if I take both of those two lines together? That's called a system. That's what we're going to talk about today. Anytime I take more than one equation lumped together, that's called a system. What would the solution of that system be? Okay, it's going to be the one point in this case. It's going to be, well, it's going to be all the points. In this case, there's only one. It's going to be the collection of all the ordered pairs that satisfy both equations at the same time, right? It has to be a simultaneous solution. And there's only one point that does that, and that's the point right there, 3, -2. Okay? Give me 1 to 5 on that. Does that make sense? Okay, so when we're talking about a system, again, system definition, and these are just, here's the handout I just gave you. It's just more than one equation taken together. If a system has one solution, well, we just saw what that looks like. That just looks like an intersection at one point. What would it look like if a linear system, and when we're talking about systems here, we're going to talk about linear systems. We could talk about more complex systems, and we will later, but we're going to talk about systems of linear equations. So the graphs are always lines, right? Make things a little simpler for now. How could I have a linear system with no solutions? Okay, that, right? That's the universal sign for parallel, right? So I get two parallel lines. Oops. Well, that doesn't look very parallel, does it? I gotta do better than that. Oh, there you go. Okay. Two parallel lines. How could I have an infinite number of solutions? Okay, if the lines overlap, right? If they end up being the same line. So something like this. Something like that. You get the idea, right? If they overlap completely. So those are the different ways that those are the different ways that a system could develop and produce solutions, different types of solutions. Okay. So there's different ways we can solve these things, and that's really what this section is about, is just solving linear systems, right? Well, we can solve algebraically, and that's what we're mostly going to do, is solve systems algebraically. We're going to learn, you guys remember doing substitution and elimination. Well, we're just going to, remind you about how all that works, substitution and elimination. But we can also solve systems graphically. Now, when we solve systems graphically, that does not mean using graph paper. Do you see why using graph paper is a terrible idea, right? Back in Algebra 1, if you did these things, probably there were some contrived problems where the lines happened to cross at convenient places, right at one of the hash marks on the graph paper. How often does that really happen? In real life, almost never, right? If you're actually doing something, if you're using math to represent something, what are the odds that the two lines in the linear system are going to cross at the exact place you want them to? No, usually they're going to cross at some bizarre decimal number. And how in the world are you going to get an accurate solution by graphing lines by hand? You just can't do it. It's just a waste of time. So what do we do instead? If we want to solve by graphing, how are we going to do that? Yeah, we're going to use technology. We're going to use a TI-84, a graphing calculator, or we're going to use Desmos. For us, we'll probably just use Desmos. Again, anybody have a TI-84? Okay, so if I'll show you how to do it. If you have a TI-84, I want to show you how to do it, but maybe I'll do that. I'll call you up during a workshop or something and just take 5 minutes to show you, because it's important to know this stuff. You can use the TI-84 on the SAT test and some, it's useful to know how to do, but maybe I won't do it for everybody if only one person's got one of those. I'd get one if I were you. If you don't have one and you're planning on taking the SAT test, I'd get one, because I will show you all these tricks. Okay, so on technology, let's see how this looks. Everybody pull up Desmos. And when you pull up Desmos, here's what I'd recommend you do. Here's what you should bookmark. If you just Google Desmos, just go to desmos.com. This is honestly the page you should bookmark right there. Because when you go to this page, this is like the central Desmos page. And look, you can click on any of these math tools, right? we're going to use the graphing and the scientific. The matrix calculator is, I don't think, again, that's a topic we may come back to. I'd really like to. I really like to how to look at how do we solve bigger linear systems using a matrix calculator. Gosh, I'm almost tempted to say we need to do that, but I'll talk to Mrs. Jones and we'll coordinate and we'll see what we think about that. But this way you can choose graphing or scientific. It's all in the same place. Well, we want graphing here. Okay, so we want to graph. Where is this thing? I had this all set up. Not there. Oh, right there. Yep. Okay. So graphing calculator. Using Desmos, it's so simple. All you have to do is type in the equation exactly the way it looks. You don't have to solve for y. These are already solved for y. Using a TI-84, you always have to isolate the y to graph any function. So Desmos is easier in many ways. So we just go y equals, and go ahead and just pull up Desmos and just do this with me. Y equals negative 5/3 x minus 6. Oops, see what I did? After you do the 5/3, what do I need to do now? Yeah, good. I can hit just the right arrow is the easiest way to do that. The right arrow on the keyboard just pops me out of the fraction, x minus 6. So there's one line. Pop down to the other one, 1/6 x. Oops, I got to do y equals. Y equals 1/6 x plus 5. And to find the intersection, well, there it is. How easy is that, right? I know the ordered pair then. That's it. It's 6/4. Okay. That makes sense? Give me 1 to 5 on that. Piece of cake, right? No big deal. Okay. Just try that one on your own real quick. Okay, give me thumbs up if you get the answer I've got up there. You know when you got it. Okay. I'm waiting for thumbs up from everybody here. Okay, got it? Okay, good enough. All right, so how about this one? Try this one. Now this one's going to be a little bit different. Try this one. Oops. So again, I can just type it in exactly the way it looks. Like that top one's in standard form, right? Is that what you got? Okay, what's that mean? Say it again. No solution. Okay, how come? Because they're parallel? Okay, how do you know they're parallel? Because they don't overlap. Okay, but you see, do you see that my question here? Like, okay, and how do you know that, Thaden? Okay, good. So Thaden, he took an algebraic approach and he solved for y in both those equations and found that the slopes are both negative 1/2. So the slopes are the same. Now, what if we didn't how could we tell graphically though? Like how could we tell just from the technology? Okay, I want you to notice something. If I go back to that previous example where the lines intersect, can you see that when I click on one of these lines, at the point of intersection, it gives me a light gray dot at the intersection. And if I click on the red line, it also gives me a light gray dot at the y-intercept and the x-intercept. So Desmos knows, it's smart. It knows to put that light gray dot any place where a person might be interested in knowing the coordinates of a point, right? And then I can go click on those dots and those points will stay on the screen then if I want to, right? So in this latest example where they appear to be parallel, there's a strategy I could use. If I click on one of the lines, like the blue line, for example, look, I get gray dots at the intercepts. If I zoom out far enough, if they intersect, I should see a gray dot. Everybody agree? Okay, and I'll prove it to you. Like, let me just change this bottom line just slightly. Instead of being negative 1/2 x, I'm going to make it negative, I'm going to make it negative 49/100. Okay, so now it looks like if I just zoom in here, they look pretty parallel, don't they? Right? But if I actually, let's make it 499 thousandths. We'll even make it even closer. So it's almost 1/2, but it's just slightly off. Okay, I clicked on the red line. I can see those dots. If I keep zooming out, boy, they look parallel, don't they? They sure. Oh, but look, eventually I see a dot where they intersect, right? You see my strategy here? If I zoom out and I still don't see any gray dots, then I know that they're parallel. So there is a way you can even check without doing any algebra. I don't know if I explained that very well. You get the idea? Right? If they intersect, I have to see it when I zoom out. So if I don't see it when I zoom out, they're parallel. Okay? All right. Let's take a picture of that one. Our notes. Ooh, that's a little big, huh? Okay, next one. Try this guy. Give me thumbs up when you got it. Let's have a race. Got it. What'd you find? Oh, okay, so they're the same line, aren't they? Right? They sure appear to be. Well, how could I tell? If I turn the red line off, the blue line is right behind it. Turn the blue line off, I get the red line, right? Okay. If I zoom out, what do you notice here? I can see that I start to get like Desmos kind of breaks because it should have just an infinite number of intersections, but I can see it starts to give me lots of intersections. So yeah, I know for a fact that lines can only either intersect no times, one time, or an infinite number of times. There's no in between. So if Desmos is showing me more than one intersection, then it means that the lines do in fact overlap, right? They're not just extremely close, okay? All right, so I guess better take a picture of that, huh? Okay, so now we've talked technology. Now we're going to talk algebra. Okay, how can we do all this stuff algebraically? So the one technique we're going to look at today is substitution. Substitution, you remember how to do substitution probably. If we've got a system, we're just going to solve one equation for y or x. So we're going to isolate a variable in one of the two equations and substitute into the other equation, right? So in this case, y is isolated in both equations. So the first step's already done. We just pick one to substitute. I'm going to pick the bottom one, arbitrarily. So we're going to substitute the bottom one into the top one. Every time you use a substitution equation, you're going to make a substitution to solve a system, put a box around it. Okay, and there's a reason for that. You'll see why, because we're going to come back to that equation. So that means in the top equation, every place where I used to have a y, that's now going to get replaced with x minus 9, right? So I end up with x minus 9 substituted for my y equals negative 7x minus 1. Well, that's easy, right? After I make my substitution, now I've got a linear equation with only one type of variable, which you guys are pros at, right? We've been doing that for a long time. So what would I do to solve for x here? Okay, good. I got to collect like terms. I'm going to move the x's to the side where I have a positive number of them. So we'll move the 7x over here by adding 7x to both sides. Okay, let's combine steps here. If I'm moving the x's to the left, where do I want to push the numbers? To the right. Good. So we'll add 9 to both sides. That's good. Then I cancel the numbers on the left side of the equation, and I cancel the variables on the right side. And look what I get. X plus 7x is 8x. Negative 1 plus 9 is 8. So we get the solution x equals 1. Am I done? No, because I'm solving a system, right, with two variables. So my solution has to look like an ordered pair, a value of x and y. So where do I go to find y? That's why I put a box around it, right? Because I'm going to go back to that substitution equation. So I'm going to plug the x in there, and I get y equals, instead of x, I get 1 minus 9. So y equals what? Negative 8. Right? And I take both of those together as an ordered pair, and my solution is 1, negative 8. Okay. Yeah, I gotta go. Sorry. Any questions? Make sense? Give me 1 to 5 minutes. You remember doing all this stuff from last year and the year before? Okay. Coming back to you. All right. How about this one? Is substitution. Oh, and I guess let's review the last couple steps, right? So we isolate a variable, we substitute, we solve the equation for the one variable I get, and then I substitute back into the boxed equation to find the other one, right? Okay, substitution is only a good idea if it's easy to isolate a variable. So what that means is we really only use it if there's an x or a y that has a coefficient of 1 or negative 1, okay? So is there one in here that's easy to isolate, an x or a y? Anybody see an x or a y that's really simple to isolate? Which one? Bottom y. Okay, good. And again, the coefficient there is 1, so it's easy, right? No big deal. So all I have to do is subtract the 7x to the other side. And if I do that, look what I get. Y equals 22 minus 7x, right? Or I could write that as negative 7x plus 22. Doesn't matter. Either way. There's my substitution equation. Now what? Okay, so I don't have to isolate y in the top. I don't have to, because that'd be hard to do, right? I'd end up with fractions, and we don't want to have any fractions. What do I do after I isolate y in the bottom? I substitute into the top. Good. So whatever I get when I isolate y in the bottom, I'm going to substitute for y in the top. Okay, what's that going to give me then? If I take that top equation, 6x minus 5 times y. And if I'm making a substitution, I always open up a set of parentheses where I can drop the substitution in. So what used to be a y is now a 22 minus 7x. Does everybody see why I need the parentheses there? Because the negative 5 is being multiplied by everything inside the parentheses, right? And that all is equal to negative 28. But that's easy again, right? I just have to distribute and collect like terms, and it's no big deal. So if I distribute the negative 5, I get 6x minus 110 plus what? Negative 5 times negative 7 is going to give me plus 35x equals negative 28. Everybody good? I collect like terms. 6x plus 35x is how many x's? 41. So 41x minus 110 equals negative 28. So what are the last two steps to solve for x? Okay, good. Add 110. Good. So if we do that, okay, that gives us, those guys cancel, and I get 4x equals 82, or 41x, sorry. So what's x equal to? 2. There you go. If I divide by 41. X equals 2. Am I done? Nope. Where do I go? Okay, good. Right there, boxed equation, right? And why the boxed equation? Because it's already solved for y, right? So if I plug that value in, what do I get? So I get y equals 22 minus 7 times 2. And that gives me y equals 22 minus 14, which is 8. Okay, and so we get the ordered pair 2, 8. Okay, good. Okay, is this a good equation to use substitution on? No, terrible. There's no variable that's easy to isolate. So we would not use substitution. We would use elimination, which is the topic for tomorrow. Okay, assignment's up. Got a little time to work. I'll let you have at it. What would happen if I got an answer like this?
At this time, we need all sophomores that have not gone out to the bus evac drills to head out front. Again, all sophomores that have not gone out need to go out and do bus evacs. Thank you.
Boy, this thing's not right at all. What if I get something like 0 equals 0? What would that tell you if I solve a linear system and while I'm solving it, I get an answer like that? It's true. So what does that mean? What's that mean, do you think? What do you think? No, if I get a true statement. Okay, yeah, it means there are infinite solutions. And so what would that, infinite solutions corresponds to lines that do what? Yeah, that overlap. Okay, so this would mean infinite solutions. Which is, what if when I solve a system, I get something like this? I end up getting the answer something like 0 equals 1, which is false. No solutions. So what's that tell you about the lines? Parallel. Yeah. Okay. Now you can have at it.